Hello and welcome to my home office. I am Dr. Joel Rosenfeld, and I am here to talk to you about generalizations of weighted composition operators, and these in particular are connected to dynamical systems. I am an assistant professor at the University of South Florida in the Mathematics and Statistics department, and previously I had spent about 6 years as a postdoc or a research scientist in engineering departments, and so this gave me a lot of exposure to things in systems theory and control, which heavily influences my current research program, and it helps me find some new problems that I can transport back to operator theory. I would like to thank the organizers, Rachel Norton and Kelly Bickle, for inviting me to give this talk. There are plenty of great mathematicians out there that they could have selected from, and I feel privileged that they invited me to give this talk here. They also allowed me to do a pre-recording because my children, they're kind of noisy, and so I have to do all of my talks and recordings and lectures in between baby nap times, or just when they're in bed in the middle of the night. So this gives me a lot of flexibility, and it allows me to give you guys a good presentation without screaming toddlers in the background. Anyways, so I would like to start with just talking about some motivation for the problem. So ultimately, we're going to arrive at some sort of weighted composition operator or a generalization of it. But before we get there, I want to talk to you about what brought me to these operators. So this is a collaborative work with several engineers and mathematicians. So I've been working with Hrishikesh Kamala-Porkar, Taylor T. Johnson, Benjamin Russo, and my wife, who is a neuroscientist, L. Forrest Gruss Rosenfeld. So the general problem that we're trying to do is sort of like data-driven discovery and modeling of dynamical systems. When we say data-driven, usually what we mean is we're talking about data we collected from snapshots of a system. So you've been observing a system and recording things like its position or voltage or other things like that, and you collect these into a time series data set. Now, what you'd like to do is be able to take that data set and extract some governing principles. So what these methods allow us to do is to come up with sort of a prediction of what the system's going to do next, but you can't just do that by only looking at the data. You need to be able to extract some information out of it, and the way we do that is using operators. So one of the principal ways of doing this is called dynamic mode decomposition, and in particular what we're going to talk about today is kernel-based dynamic mode decomposition, which was introduced by Williams et al. Back in, I think, 2015. Basically what we're going to be doing is you take a look at your snapshots, and you have, say, x0 leading to x1, leading to x2, leading to x3, and etc. And you're basically thinking that this is a discrete time system that is evolving, sending x1 to x2 to x3, and these become samples of your dynamics. For most of the problems that we were concerned with, we were really looking at a nonlinear system. And when you want to convert nonlinear data to linear data, you go ahead and you take a nonlinear system, say a finite dimensional nonlinear system, and what we're going to do is we're going to transport it into an infinite dimensional system where we can employ linearity. And the way we're going to employ linearity is by looking at operators. So in this case, we start with the composition operator. We also call this the Koopman operator. So essentially what we're going to do is we're going to take a look at our data set, and we're going to look at it through the guise of what are called observables, or say functions inside of some sort of Hilbert function space, usually a reproducible kernel Hilbert space. And then if you hit that observable with the Koopman operator, and then you evaluate it at xi again, it's basically going to give you G composed with F being your discrete dynamics acting on xi, which is the same as G of xi plus 1. And so now we have an operator that represents our discrete time dynamics through the symbol of this composition operator. Now, we don't know what the discrete time dynamics actually are. We don't have access to F. What we have access to is this collection of snapshots, and now we're looking at it through the guise of these observables. So now what we would like to do is we would like to be able to construct an approximation of the Koopman operator using these snapshots and in our Hilbert space setting. Now, I find it a little bit more convenient to not talk about observables, but to look at the action of the Koopman operator, or the adjoint of the Koopman operator, on the kernel functions. If you do any composition operators, and I know a good number of you do, you'll know that the adjoint of a composition operator acting on a kernel function advances the center of that kernel function from, say, a center at z or x to f of z or f of x. Z if you're in complex plane, and x if you're just talking about real variables. So what does it tell us? It tells us that we know the image of the adjoint of this Koopman operator on a kernel function, and we don't need anything else other than the dataset itself. So what we can do is we can use some Hilbert space concepts and talk about projections onto the span of these kernel functions, and we can construct a finite rank representation of this Koopman operator. So that gives us a finite rank representation of our Koopman operator. Now we can use this in order to get a model for the system, and basically the idea is that we're going to be taking a look at the eigenfunctions of this Koopman operator. We'll assume that the Koopman operator itself is actually diagonalizable. Under this assumption, if we take the identity function, which again we're assuming that the identity function is itself in the space. When I say the identity function, I mean the function that maps x in Rn back to x. And now what we're going to do is we're going to take this identity function, what is known as the full state observable, and we're going to decompose it in terms of the eigenfunctions of the Koopman operator. When we use this eigen decomposition, the coefficients we end up calling the coefficients Koopman modes. And if you take a look at any of these eigenfunctions acting on a snapshot from our system, you can actually go ahead and use the eigenfunction identity for it, and the fact that the Koopman operator is the composition operator, and you can get this relation where basically it says that the eigenfunction evaluated at xi plus 1 is equal to lambda times the eigenfunction evaluated at xi, and then you can spin this out, and then you basically get the eigenfunction at xi plus 1 is lambda to the I plus 1 of the eigenfunction at x naught. So then we can go ahead and take a look at our full state observable expansion, and if you put the snapshot into the identity function, you can see this cascade through the series representing the full state observable, where you can now just talk about the eigenfunctions evaluated at x naught, and we have now an expression in terms of exponentials of the eigenvalues. Now, we don't always have access to these eigenfunctions of the Koopman operator because we're only dealing with the data, and again, we don't know what f is. So we can go back to this finite rank representation, and we get these sort of stand-ins where we take an eigen decomposition of this matrix, and that will lead to these sort of approximations of our eigenfunctions. And this leads us to the data-driven model for our dynamical system. Now, you run into a whole lot of issues here. First of all, we've only...
Okay, so I was editing that video. I realized that it was going to be more than an hour of me chatting about nonsense. So, what are the real problems here? We have that Koopman operators are almost never compact, so that means that representation we just made is never going to actually converge. The best kind of convergence results we have for the Koopman operator is strong operator topology convergence, and that just uses the fact that the Koopman operator is bounded. Now, the other problem we have is that not every continuous time dynamical system is actually discretizable. So if you have something like s dot is equal to 1 plus x squared, that gives you a tangent. And you pick a step size for your discretization, there's always going to be some point that's going to send you to infinity. And that's not allowable for a composition operator. So in order to take care of this discretization problem, first what we need to do is we need to change the operator to a Liouville operator. Liouville operators are a sort of more general version of what are called Koopman generators, and they sort of exploit what is called the orbital derivative. Now, when you use these Liouville operators, they are unbounded. So it's worse than the non-compactness of Koopman operators. Assuming you can even find a bounded Koopman operator, I mean, Liouville operator is going to be worse than that. Okay, so how do we take care of the compactness? To start, though, actually we want to still be able to get a finite rank representation of this unbounded operator, even though it's not going to be a great thing. And so what we're going to do is we're going to use what are called occupation kernels, which are integration after composition with a trajectory that satisfies the dynamics. When this happens, you actually get that the adjoint applied to these special functions end up giving you a difference of kernels. So that's fantastic. You can still get a finite rank representation, but how do we know this is ever going to converge? I mean, it's not a compact operator, it can't converge, right? So what we do instead is we turn into weighted composition operators for the answer to that. So we saw that over the Fock space, a weighted composition operator can turn a multiplication operator into a compact operator. And there's a lot of authors who have investigated weighted composition operators over the Fock space. And so we want to spin off of that and see if we can do the same thing for these Liouville operators, which are unbounded just like multiplication operators are over the Fock space. So what we do first is we compose. Now the first thing that me and my co-authors thought to compose with was just A times Z. Easy enough, we call those scaled Liouville operators. And the reason why we do that is that if A is close enough to 1, we actually don't affect the data hardly at all, at least not up to computational precision, but we end up getting a compact operator. So that's one example of a Liouville weighted composition operator. And if you just change AZ for some phi of Z, the boundedness and the compactness of this operator actually tells you what happens to phi. And so this is something I'm working on with my graduate student, Himanshu Singh, and Benjamin Russo. And so you can basically get some sort of adjoint relation on the kernel functions, and then use boundedness to make this ratio less than, say, a constant, say m, take the logarithm of both sides, integrate around the circle of radius r, and ta-da, you see that this relation leads to you having a power series expansion of phi with respect to r squared. And if r is allowed to become unbounded and there's nothing keeping it from being so, we'd get infinity is less than m, log of m. So there you see that the only way that this can work is if that r squared term is the coefficient on the r to 2m is 0. Or it ends up being annihilated by the r to the 2, or it ends up being annihilated by r squared, which came from the kernel function in the denominator. And then this tells you that phi must be affine. And so that's a nice little result. And so, so this is what we call a Liouville weighted composition operator. And yeah, we like, and then you can build some more stuff off of this.
Okay, so let's go ahead and get into the vector valued portion of this. So I promised we would talk about vector valued reproduced kernel Hilbert spaces, which are basically reproduced kernel Hilbert spaces with functions that take that are vector valued. I'm not going to get into too much of the definition there, but just keep that in mind. The dynamical systems that these correspond to that I care about are control affine systems. These are systems of the form x dot is equal to f of x plus g of x times u, where u is a control signal. Basically, you choose a control signal, and then that will influence what the state does down the line. So what you would generally like to do is you would like to figure out what f and g must be. And we're going to do this by encoding the control trajectory and the controller inside of what we call a control Liouville, a control occupation kernel. Now, once you do that, you can take something called a control Liouville operator, and you can actually get a finite rank representation of it. This control Liouville operator is an operator that sends a scalar valued function to a vector valued function. And it does it by taking, say, h to h prime times this row vector f comma g. And when it does this, you can basically get a decomposition of your drift dynamics, which is the F, and the control effectiveness, which is G. Now, ultimately, what we want is we want to get a model out of this, and this control Liouville operator on its own can't do that because there's no dynamics there to analyze. You don't have dynamics without inputting a controller. So you need to figure out a way to put a controller in there, and this comes from a multiplication operator. In particular, we can get a multiplication operator where we multiply this control Liouville operator times some column vector where you have one in the first slot and say psi of x in the second spot. This psi of x is what we call a state feedback controller, where you make control decisions based on the current state. Now, when you combine these two operators together, what you get an actual Liouville operator at the end of the day. And so with this, we can go ahead and do our finite rank representation and do a decomposition. And so, but since we have removed the decisions about F and G from the system itself, from the controllers itself, now we can implement new controllers that we've never seen before. But we'd still like to have a compact version of this. So we can either put a composition operator before, say, the control Liouville operator, or we can put a composition operator before the multiplication operator, and both of these will give you different Liouville operators on the other side. And with certain decisions that you can make, you can ultimately get a compact operator that you can decompose and that it won't also mess with your data too much. Okay, so I think that's a good place to stop. I didn't mean to make this a rocket through operator theory over dynamical systems, but I hope you learned something. I have a longer version of this talk that I'm working on, and it may be in a month or so. I'll post it to my YouTube channel. And so if you want to check me out, go to www.thatmaththing.com, and or you can go to my lab website, which is www.thelearningdoc.org. And so thank you for watching, and have a great day.